Bismillahirrahmanirrahim. Today we are going to discuss color of the transition metal complexes. Why transition metal complexes are colored? Here is the answer of this question. First of all, I am going to explain electromagnetic spectrum. Electromagnetic spectrum is the combination of different radiation. For example, gamma rays, X-rays, ultraviolet, visible rays, infrared, IR, and radio waves. In this spectrum, only the visible region, as the name indicates, is visible to the human being eye. The rest of the all radiation, gamma rays, X-rays, ultraviolet, infrared, and radio waves cannot be seen by the normal human eye. So, any object, if it is reflecting or it is transmitting the light, the radiation that is lying in this region will be a colored compound or will be a color that will be showing a color. Let's talk about visible spectrum. In visible spectrum, there are basically 7 bands colors. Number 1, there's a violet color, then indigo, blue, green, yellow, orange pattern, and the rest of the all portion are said to be the red portion, red in color. Wavelength that is starting from 400 nanometer to till 780 nanometer. As we move left to right in the spectrum, from violet to indigo to blue, green, yellow, orange, and red, basically wavelength is going to increase. As the wavelength is increasing, photon energy or the energy of this band is going to decrease. So highest energy belongs to the violet color and the lowest energy belongs to the reddish compartment. When photons, white light, allowed to pass through any solution, some part of the light is absorbed and rest of the part of the light come to the eye of the viewer. That is the color of that solution. For example, in this complex, you can see the color is appearing as a blue color. There are 2 possible reasons for this color. Number 1, either this substance, this complex, this solution is not absorbing this one bandwidth. So it's not absorbing the blue color light. It is appearing as a blue in color. And rest of all the portion is being absorbed by this compound. The second one explanation, the possible explanation that could be, it's absorbing some portion of the red color. It's absorbing the some portion of the red color spectrum, and rest of the all colors are mixing together to make a new color that is said to be the blue color. So there are 2 basic possible reasons for the color of the transition metal complexes. Either it is not being absorbed, that portion, that color is not being absorbed by that complex, or any other color that is being absorbed give a complementary color. If it is absorbing the red region portion and the rest of all colors are going to mix together and they are constituting blue color to the eye of human being or the eye of viewer. When white light hits a substance, it may be absorbed or transmitted or it may be reflected. So there are 3, once again, major possibilities. When white light hit the substance, it may be absorbed, it may be transmitted, or it may be reflected, wholly reflected towards the eye of viewer. If all incident white light is being absorbed, then the substance looks black. Then its color will be the black. If all incident white light is reflected by that substance, it will look white or it will look grayish in color. If only small portion of the incident light, white light, is being absorbed and all the radiations in the visible region of the spectrum are transmitted equally, then substance will appear colorless like a water. So in this case, in this sample, almost a very few portion of the visible light is being absorbed and most of the portion is not being absorbed, or you can say that is transmitting by this sample. So this sample is looking like a colorless sample. In case of transition metal ion, electrons of the d orbital transit from low energy to high energy state after absorption of photon and making the complex of these transition metal colored complex. For example, an aqueous solution of copper 2 ions is light blue in color. It means that it's absorbing, once again, as I have told you, it's absorbing some portion of the red light, or it is not absorbing the blue region of the spectrum. So that's why its color is appearing as a blue. Now let's talk about the complexes, their geometries, and the different colors. Before making the complex, any transition metal ion is showing or said to be having degenerate orbitals. For example, in case of copper, it's having 5 orbitals, that is the 3D orbitals, and these all 5 3D orbitals, dx square dash y square, dz square, dxy, dyz, and dxz or dzx, they all are lying at the same energy level. So it means that if the orbitals are having same energy, they are said to be degenerate orbital, or we can also said to be hypothetical degenerate orbitals. This is the story before making any sort of complex. In pure copper metal, these orbitals are lying on the same energy axis. This copper metals, usually as far as A2 syllabus is concerned, Cambridge syllabus is concerned, there are 2 possible complexes. One is said to be the octahedral complex, and other one is said to be the tetrahedral complexes. When these metal ions react with the different ligands, they may make octahedral complex, they may make tetrahedral complex. For example, tetrahedral complexes. CuCl4 2 negative ion is the tetrahedral complex. In this case, once again, pure copper before making this complex is having 5 d orbital. Those are lying at the same energy axis. I mean, they are hypothetical degenerate orbitals. When ligand make the dative bond with the Cu2 positive ion, let's suppose 4 Cl negative ion are going to make the bond with copper ion, then there will be no more degeneracy for this copper d orbitals. This set of d orbital, those are initially degenerate orbitals, they will split into 2 energy level. In case of tetrahedral geometry, 3 will raise their energy as compared to the rest of the 2. So it means that these 3 orbitals are experiencing more repulsion from the electron of the ligands. So they are going to raise their energy. Here the difference of energy is denoted or said to be delta E. It is also known as crystal field splitting energy. Then when the white light is passed through the complex, then some of the portion of the white light is absorbed, and that cause the transition of electron from low energy orbital to the high energy orbital. After that phenomena, the rest of the color make a new color of the complex that may be any other color. The next one is octahedral complexes as well. Transition metal make octahedral complexes, and once again, initially they all are having same energy d orbitals. In this case, a copper 2 positive ion, that is an isolated copper 2 positive ion, is having 5 d orbitals, and they all are lying at the same energy axis. This copper ion is having 9 electrons at the moment. So in this case, this 3D is having hosting 9 electrons. So these 9 electrons in 5d orbital are lying at the same place. When copper ion make the aqueous complex, aqua copper 2 positive ion, then there is a splitting of the formation of the dative bond. Once again, splitting occur in these 5 orbitals. Now this time, due to the octahedral complexes, the 2 orbitals are going to raise their energy. These are said to be dx square dash y square and dz square. These are dx square dash y square and dz square orbital, and the set of 3 orbital, they are dxy, dyz, and dzx, you can say. So if the geometry of the complex is octahedral, then these two square, I mean those are expressed by the square, these 2 orbitals are facing more repulsion. These two orbitals, the orbital, those are exactly lying on the x-axis and y-axis and z-axis, so they will feel more repulsion and they will raise their energy. Once again, this energy difference is denoted by delta E, and it is said to be the crystal field splitting energy. When the white light is passed through this complex, some of the portion of the white light is absorbed that causes the transition of electron from low energy orbital to the high energy orbital. Now, one electron, you can say, that has been shifted from low energy to high energy compartment. So after the absorption of some radiation, rest of the radiation, those are not being absorbed, will constitute a new color to the eye of the viewer. So this is the simplest story how complexes, different complexes, octahedral complexes and tetrahedral complexes make the different colors. How to report the answer? Here are the basically four major postulates at the point to report your answer. After formation of the complex, d orbital of the metal ion split into two energy states because repulsion between the electron of the ligand and the d orbital. That is the main cause of the splitting of the d orbital. That is the reason of disturbance in the degeneracy of the d orbital. The second one is the geometry of the complex. If the geometry is octahedral, then dx square dash y square and dz square orbital go to the high energy level as compared to dxy, dyz and dzx orbit. If the coordination number is equal to 4, in case of tetrahedral, not the square planar one, the dxy, dyz and dzx orbital go to the high energy level with the same pattern. When the white light is thrown on the complex, electron from the low energy orbital or lower energy orbitals absorb specific part of the portion of the light or the photon and jump to the vacant high energy orbital. So rest of the component of the white light make a complementary color of the complex to the viewer. So these are the basically, you can say one of them, 2, 3 and 4 major postulate to report your answer for 3 to 4 marks, that why complexes of the transition metal ion are going to make the color. Now the next one question is, what is the reason for the different colors? Why different complexes are going to make the different colors? Number one, if they are having different metal ions, color will be different. Due to different oxidation state of the metal ion, color will be different. If they are having different nature of ligand, different type of ligands, color will be different. And these all factors are going to change the splitting energy gap. They are going to change the splitting energy value of the two energy level. For example, I'm going to write 3 different complexes. For example, iron Fe(H2O6) complex. This complex is basically green in color. The solution of this complex is green in color. I mean, it's an aqueous complex. The next one is CuH2O6, that is hexa aqua copper complex, and its color is blue. Its solution is blue. Its aqueous solution is blue. The next one is FeH2O6, 3 positive ion, that is reddish brown in color. So these 3 complexes all are having different colors. Why the first 2 complexes are showing different color? Basically, number of ligands are same, nature of ligand is also same, even charge on the complex and charge on these 2 metal are also same, but the color is different. The reason is there are 2 different metals. This is the iron and this is the copper one. And if we are going to compare the first and the third one, I mean green and the reddish complexes, in this case the iron, both are having the same metal, that is iron metal, but the first one is having iron plus 2 oxidation state, and in this case this complex is having plus 3 oxidation state. So the oxidation state of metal ion does matter whenever you are going to check the color of the complexes. Now I'm going to compare one blue and one the reddish one. In this case, once again, there is no change of ligand. There is the change of simply the metal ion. I'm going to write another complex, for example, Cu, and that is Cl4 2 negative ion complex. This complex is basically yellow in color. Now, in this case, you can see that the nature of the ligand are changed. As comparison with the blue complex, and this the copper is same, I mean transition metal ion is same, but the difference is with H2O and Cl ligand. So if metal ions are different, then color will be different. If oxidation state of the metal ions are different, even they belong to the same element, color will be different. And if the nature of the ligands are different and number of the ligands are different, you can say the color will be different. So nature of ligand, number of ligand, metal ions, and oxidation state of the metal ion, they all basically contribute to the different color of the complexes. Now come towards the prediction of the color of the complexes. Just have a look on this picture. You can see that this diagram is showing almost purplish, deep purple color or the purplish color. There are the two basic reasons. Number one, this complex is almost not absorbing in the region of violet compartment and the violet region. And it's showing the maximum absorbance, so it's a deeper complex. Its color is deeper because it is showing the maximum absorbance. It is absorbing the maximum number of wavelength, so its color is deeper. The next one, the second one, you can say that you can predict it from the color wheel. This is the color wheel that is showing the 7 band colors. For example, we are having 7 colors of the VIB-coil, I mean the white light components: green, yellow, orange, red, violet, indigo, and blue. So if the any complex that is absorbing the light in, let's suppose, in yellow color region, it will show its color will be violet, you can say. If any complex is that is absorbing the light in the region of orange light or in this wavelength compartment, then its color may be like indigo or light violet, you can say. If any complex that is showing some portion of the red light, its color may be the bluish one. Or any complex that is showing the green, exhibiting the green color, it's showing, it's emitting it's green in color. So it is true that it will absorb some portion of the red compartment and some portion from the violet region. So this is the approximate prediction of the color by using this color wheel.
Let's solve the past paper questions. Question number 6, part B. Complete the diagram to show how the presence of ligands around an isolated transition metal ion affects the energy of the d orbital. Here is an energy scale diagram. There are degenerate d orbitals over here, and he is asking to draw the two specific complexes. In case of tetrahedral complexes, this d will split into two energy level, but 3d orbital will raise its energy as compared to the rest of the two orbitals. In case of octahedral geometry, once again there is two type of splitting. These are two orbitals, set of two orbitals. These are basically dx square dash y square, and this is dz square. They will raise their energy as compared to the rest of the orbitals. Those are said to be dxy, dyz, and dzx. Explain why transition metal complexes are colored. And the marks are 2. Total 2 marks are there for this question. So I'm going to explain the more specific part of the question, more specific reason. A very comprehensive reason should be written over here. And the comprehensive reason is, first of all, when white light is thrown on the complex. When white light is thrown on the complex, some of its portion is absorbed. Some of its portion, its part, is absorbed. That causes the promotion of electron from low energy orbital to high energy orbitals. So the one mark is for absorption, light is absorbed. The second one mark is for the promotion of electron from low energy to high energy orbital. So that's why they are giving the colors of different compound. The next one is hexa aqua copper 2. Positive ion complex is pale blue, but this tetraamino diaqua copper 2 complex is deep purplish blue or purple blue. For basic reasons. If the metal ions are different, then color will be different. Oxygen state of the metal ion is different, color will be different. Nature of the ligand is different, color will be different. Even type and number of ligands are different, color will be different. And they all are going to change the splitting energy and so on. So once again, I'm going to report my answer. In this case, basically, the ligand is different, so I'm going to write it over here. Both complexes have different ligands. Both complexes are having different ligands. So they are having different energy gap between the splitter d orbital, or so they will absorb different frequency of light. They will absorb different frequency light. Or you can say because of different energy gaps between the orbital. Gaps between the orbitals. The next one is part C. Diagram shows the visible spectrum of the solution, that is hexa aqua vanadium 3 complex, and state and explain the color of the solution. Basically, as you see that in this case, the most unabsorbed portion is the greenish portion. This portion is not being absorbed, almost, you can say that is green in color. The color of solution is most probably will be the green solution. Explanation. For explanation, we can write as number 1, there is the least absorbance of green, and the highest absorbance goes to for blue and red region. And blue and red colors are going to absorb in high intensity. So here is the answer of this question. I mean, for 1 mark this color, for 1 mark for this explanation. Basically, as I told you that you can predict the color from the color wheel approximately, and it's absorbing the blue and red at the maximum level. If the blue and red are going to absorb up to the maximum level, then its color will be green. If the violet and red colors are going to absorb, then its complementary color, its opposite color is the greenish one. In this case, we will write the approximate answers, approximate colors. There are two isomeric complexes with the formula CrMH4Cl2 positive. One is green and other one is violet. Suggest the type of isomerism shown by these complexes. These complexes may show cis-trans isomerism. That is another topic you can say. Cis-trans isomerism. It can show cis-trans isomerism. Explain why these two complex ions are colored, and the second one is why are going to have the different colors. So the first part is basically why they are showing the color. There is a general reason why they are colored. Number one, d orbital split into two energy state. Split into two energy states when ligands makes the bond. Ligands make the dative bond with metal ion. When ligand make the dative bond with the metal ion, then d orbital split into two energy state. Again, when the white light is thrown, or the light is thrown, when light is thrown on the complex, some of its part is absorbed that causes the promotion of electrons from low energy orbital to high energy orbital. So this is a specific reason for 2 marks. The next one is, again, why they are having the different colors. Then they both are having the different complexes. They both are having the different geometry, and the general reason for the different colors is DG energy gap. I mean energy gap. Both complexes are having different DD energy gap, or simply splitting energy gap. DD or splitting energy gaps. So if they are having different energy gaps, they will absorb the different frequency of the light. So they will absorb different frequency of light for promotion of electrons. That's all for today. Have a nice day.